My pleasure to introduce our next speaker, Professor Paul Lavery. He's a Professor of Marine Ecology at Edith Cowan University, as well as the Director of the University's Centre for Marine Ecosystems Research. He also has more than 20 years experience in undertaking research in seagrass ecosystems. Paul is the leader of the Theme 5 research program examining the effects of dredging pressures on seagrass. Thank you, Paul. It's all yours.
Thanks, Ian. So as Ian said, I'm going to be talking about the theme that focused on primary producers, the impacts of dredging pressures on primary producers and thresholds related to that. It's an overview. There were 10 reports produced out of this theme, so that gives me about 3 minutes per report. So I'm going to go over them quite broadly. What I'm really going to focus on is showing you generally what we did and try to focus on what the main implications for those findings were from a management perspective. There's going to be 4 talks tomorrow. Gary, Catherine, Simone, and I'm going to be speaking from Matt Vandercliff, which will fill in the detail. There's a cast of thousands involved in this, as you would imagine, and I'll give some acknowledgements at the end. So while it's about primary producers, the theme focused very much on seagrasses, and there were 2 reasons for that. The first is that seagrasses are recognised as being very ecologically important in the Northwest. Not that other primary producers are not also ecologically important, but also there was a general sense and recognition that seagrasses were particularly sensitive to the sorts of pressures that dredging could produce, and were likely to respond earlier than some of the other primary producers. So early on, the decision was made to focus on seagrasses. I've just put that notice up there. I'm going to present some data from Chevron later on around light data, which extended our capacity to do some of our analyses in here. Okay, so just conceptually, why are we worried about dredging and seagrasses? Very simply, on your right-hand side, you've got a picture of an environment where you've got no dredging occurring in it. You've got light coming in and plenty of light generally reaching the bottom, enough to sustain growth and reproduction of seagrasses. In a dredging scenario, sediments are put into that water column. You have a reduction in the amount of light which can reach the bottom and therefore sustain seagrasses. You also have an alteration to the quality of that light, the spectral quality, and typically that produces a bit of a shift towards a yellow-green sort of colour. As those sediments settle, as Ross has just explained, you can have a smothering effect. So the sediments can physically coat or bury the seagrasses, potentially, but they also smother the surface of the sediment, and that could introduce some biogeochemical alterations in the sediments, which could have an effect on seagrasses in terms of oxygen, sulfides, and other things. Now, those 4 mechanisms at the start of the project were believed to be the major mechanisms by which dredging could potentially affect seagrasses, and so that's where most of the focus for the theme was placed. Now, what we knew about seagrasses in the Northwest when we started was very, very little. Rudimentary. There was a few publications suggesting that there was about 11 species of seagrass up there. We had some insights from some projects that Gary and Catherine and other people had been doing at the time that the composition and the abundance of seagrasses was highly variable up there, but we really didn't understand much about it. Most of the approaches to managing seagrasses and dredging had come from the temperate zone studies that had been going on for about a decade before that. What we knew from the limited information was that these systems are very different, and we couldn't just transfer those temperate approaches up to this type of environment. There were also 2 very common views going around at the time when you talked about seagrasses in the Northwest and dredging. One was that these meadows seem to come and go. They recover naturally. Many of them are transient, so therefore they're likely to have seed banks, and that means that these things are likely to recover naturally from significant disturbance events. And the second commonly experienced view was that, or a question that was often put to you, was that these areas are naturally very turbid and highly variable with respect to their turbidity, so do we actually need to worry about dredging affecting seagrasses in these environments, because they're probably adapted to all these very high levels and highly variable turbidity anyway. Okay, so with that in mind, we then went through that 2008 process, which Ray talked about earlier this morning and in subsequent years, and identified the key knowledge gaps. And these key knowledge gaps were identified as the ones which were most important to decrease the level of uncertainty about seagrass responses to dredging. We recognize there's lots of other gaps. We also recognize that the Theme 5 project couldn't fill all of those gaps. So we focused on some of the key ones. And they were what's out there, how does it vary, how do different species respond to reductions in light or burial due to dredging? Does the type of sediment which is burying or it's suspended over seagrasses matter, whether it's inorganic or organic? Do changes in spectral quality actually matter? We didn't have a clue. How do they recover? Do they recover quickly? Can they recover? What is the mechanism of recovery? How important is reproduction, seed banks, and so on in that recovery? So the theme was structured around a series of projects, 5 projects, creatively named 5.1 to 5.5. And what these did was we reviewed the literature to understand what we knew about seagrasses in Northwest WA and the effects of dredging on them. We then did a series of 3 projects on genetics, natural dynamics, and recovery. And what these were designed to do was basically let us understand what are seagrass ecosystems in this place. And really, that's all about contextual information. Context for proponents and regulators to understand the environment in which dredging is occurring and where seagrasses are occurring. And then a very large part of the project doing a series of mesocosm-based experiments to understand the response of different seagrasses to dredging pressures and develop thresholds. So what I'm going to do is run you through some of the findings in relation to each of these. But as I go through each one of them, I'm going to try and bring the results back down to this EPA 2016 framework, which is currently what dredging management is based around in WA, and particularly talk about what are the implications of the findings for pre-development surveys, impact prediction, and post-development management and activities. Okay, so what's up there? From the reviews, we found out that, yep, there's 11 species of seagrass up there, and they're widely distributed across a whole range of habitats. We, from that review, decided to focus on 3 particular species, and we chose those 3 species for a number of reasons, including the fact that they were widespread and occur in a wide range of habitats, because they were considered to be ecologically very important as forage, as habitat, and so on. But also because by looking at these 3 particular species, Holophila ovalis, Samidosia cerulata, and Holodrila uninervis, that we were capturing a range of seagrass life history types and morphological types, so that therefore increased the general applicability of the findings across different types of seagrasses. So for the natural dynamics, we went out and we did, over a 2-year period, we surveyed a few seagrass meadows. The focus was mainly where those yellow dots are in the Exmouth region. But opportunistically, we were able to sample a few other regions further over to the east. Some good advice from Ian McProvo here about Balla Balla pointed us in that direction. And also, we were able to get some data from Chevron, from their Wheatstone project around Onslow, to have a look at some of the seagrass characteristics in that area as well. From those surveys, the first thing that we observed or found was that the abundance and the composition of seagrasses is highly variable amongst sites. And that's amongst sites that are only in the order of tens of kilometres apart. Some sites had up to 6 species, others only had 2. And if you look at the graphs here, which are graphs of percentage cover, you can see that some are getting up to 60% cover and others are staying way down at the less than 10% cover for most of the time that we're looking at them. You can also see that in the top 2 graphs, there's a sort of an annual cycle. If there is an annual cycle in abundance of seagrasses at a site, and there isn't always one, if there is one, it tends to be that the abundance is greater in summer and lower in winter. But as you can see down at the bottom at the Marian Islands, there really wasn't much difference at all. And the data from around Onslow show that the biomass was extremely low and not very variable. The little symbols up there are supposed to be flowers. So we noticed flowering. The plants were reproductive. If a site was reproductive, it tended to be in the November sampling period. But it didn't occur at all sites, and even at sites where it did occur, it didn't occur in every year. So it was a consistent time of year, but not consistent every year or in every place. What those biomass data don't show you is what was happening with the composition as well. And at that Exmouth Gulf site, over the same period, this is the same data, but showing you the abundance of each individual species that we saw there. Now, there were a couple of cyclones in about 6 months leading up to the sampling beginning, so a significant disturbance event. And subsequently, we had this very dramatic change in composition, which the dotted line shows that we were up there a few weeks ago. There seems to be those changes seem to still be ongoing. Now, this change in abundance and composition was very reminiscent of data that Neil Lonergan published in 2013, following some monitoring that he did following Cyclone Vance in 1999. Very similar patterns of massive changes in abundance and composition over 4 or 5 years following disturbance. So it seems that there's also some interannual changes in abundance and composition that could be related to major disturbance events. Another very interesting finding for us from this natural dynamics was that there's bugger all seeds out there. This table shows you the number of seeds that we found from 10 cores that we sampled. So the number in brackets are the percentage of cores that had a seed in it. The number outside the bracket is the number of seeds that we found. Okay, so not very many seeds that we found out there. And for most of the hologily seeds or fruits or seeds, for most of the hologily seeds we found, they'd actually been predated on, so they weren't viable even if they were there. So there were far fewer than we anticipated, and flowering was not regular. You couldn't predict it to be there at these sites every year. So that does not support that view or assumption that you can assume that meadows will recover from seeds. Okay, this data doesn't substantiate that. Catherine did some nice analysis using the data that had been made available to us from Chevron, and our data was simpler and a subset of the sort of analysis that Ross has just shown you, focused very much on sites where seagrasses were known to occur, to look at the sorts of changes that occur at those sites. I've just put one graph up here. The black line shows you the weekly average of daily light at a site in the pre-dredge period. The 2 lines underneath it show you the same weeks of the year in the dredging years. And what you can see is that there's a significant reduction in the amount of light at that site. And this is a high impact site, so it's very close. But as Ross pointed out, there were less significant impacts, but still detected at tens of kilometers away from the dredge site. We also did a generalized linear modeling analysis, which showed that even though these environments are naturally turbid, there was a statistically significant effect of dredging on light availability at those sites. So on very limited data, and I will stress that, one place, one dredging event, we cannot assume that dredging will not impose an additional light reduction beyond the background level. So I've put the seed result up, and I've put that one up because I think those 2 very common views that were there before we started the work to some extent have been addressed by these findings. So what are the implications of this? I think given the temporal variability, both interannual and intra-annual, pre-development surveys really need to be undertaken several times if you want to be sure you're going to capture the composition and abundance of seagrass at a reference site or a potential monitoring site. And if you've got limited time, we'd recommend that you do it in November to February, because that's when you're most likely to find stuff. because of that, is that 5 minutes? I was going to say. Because of that interannual pattern that seems to be a result of disturbance, I think it's important that when you're establishing your reference sites, you understand if it has been affected by disturbance, where it is in that post-disturbance cycle. Because otherwise it's going to be very difficult to relate your findings from a monitoring site against this site, which is going through some complicated sort of post-recovery cycle. And ideally, your reference and impact sites would be within about 20 kilometers of each other. From an impact prediction perspective, don't make the assumption that these meadows will recover from seed. They may not have much seed there. Dredging can significantly affect the light that seagrasses receive, even though the environment is naturally turbid. And because of the consistent timing of flowering, that at least opens the possibility for looking at that in the context of environmental windows, in terms of when you might want to time your dredging activities. Okay, so we then moved on to a series of experimental tests to try to look at and develop thresholds and have a look at the responses of seagrasses to different pressures, particularly light reduction and burial. And we did this in a series of mesocosm facilities. This is the mesocosm facility we ended up with. It was a part of a bit of an evolution, and I think we should stress that this is a very significant outcome of WAMSI in itself. It's the only facility that we've got in WA, really, that you can do these types of experiments in, and it's now housed at UWA. In the first experiment, we basically just established pots with those 3 species in it. The 3 species were in each pot, and then we subjected them to different levels of light reduction for different amounts of time. So a classic sort of shading experiment. We measured everything that we could measure on the things, produced tons and tons of your standard sort of scientific graphs over here, which I won't go through. Gary may show some of those tomorrow. I'm not sure what he's going to show you, but basically, in summary, what we found was that the impact depended on which species you were looking at. Different species responded differently. It depended on the intensity and the duration of the light reduction. All levels of response, from physiological through to productivity, through to plant morphology, through to the whole biomass in the pot, all of them responded to light reduction. The physiological ones responded most rapidly, and the pot biomass and the morphology variables responded most slowly. And the 4 that I've shown on the graph on the left are the ones that we ended up suggesting would make the most appropriate bioindicators. These were variables that responded consistently to increasing pressure that we put on in terms of light reduction. And because some of them are physiological and some of them are morphological and biomass, then these potentially offer you the opportunity to have early warning indicators or later indicators of an amount of impact that's occurred in a meadow due to light reduction. And these could therefore, we're recommending that these are potential reliable bioindicators to embed in monitoring programs. From those graphs on the left, if you went through them all carefully, you could pick out a light level that is about the sort of light level that, for example, would cause a loss in shoot density, a loss in biomass in a meadow. And that tended to be somewhere between about 5 and 9 moles of light per meter squared per day. When you produce a result like that, then the first question that you get when you present it to an audience that's used to dealing with dredging is, okay, if these things can cope with 8 moles per meter squared per day over a certain amount of time, can we design our dredging to give them a really high period of light reduction, way above that, but then turn it off and let them get high light so that on an average they get that amount of light, even though they're getting some very intense periods of low light? And the answer was that we didn't know at that point. So we set up an experiment to specifically address that. And just to take you through this, the top in green is we grew plants just like I'd shown you before. We had 5 treatments. The green is they were grown for 6 weeks continuously in high light. So they were getting about 8 moles of light per meter squared per day. We had a medium treatment in yellow and a red treatment in red. So these were getting continuous light. We then reproduced the medium treatment. They were getting the same amount of light on average over a 2-week period, but we gave them that amount of light in different patterns. So you can see down the bottom, scenario 1, they got 10 days of very low light, followed by 4 days of very high light. Scenario 2, they got 5 days of low light, followed by 7 of medium and 2 of high. And at the end, we compared what they looked like. If the pattern of delivery didn't matter, then the bottom 2 should have had the same outcome as the medium, as the yellow treatment. In fact, what happened was the treatment down the bottom, where they only had 5 days of continuous low light, ended up looking like the medium treatment, which is what you would expect. But the treatment that had 10 days of low light followed by 4 days of high light actually looked like the treatment which had only received continuous low light, even though on average it had received double the amount of light. So very clearly, the number of low light days that are experienced consecutively has an effect. So the delivery pattern of the light matters, as well as the average amount of light that they're getting. Now, one of the beauties about the WAMSI program, as people have said several times, is that we were constantly in touch with the Node leadership team and other people in the team. We were able to convert these sorts of results through lots of discussions, and particularly with Ray, who I thank for this, to try to turn these into thresholds and criteria. Those criteria and thresholds evolved over the project, but what we've ended up doing at the end of the project is to be able to produce a set of what we're calling impact thresholds. And these take into account both the intensity, the duration, not both, all of the intensity, the duration, and the delivery pattern of that light. And so these represent, for example, if we take the top line for Samidosia, this is saying that plant for its biomass can experience an average of about 9 moles per meter squared per day, averaged over 2 weeks for a 12-week period. It won't show much of a significant effect. But within that period, it can only have a maximum of 5 days of low light. Okay, so there's a series of thresholds there that we've developed for the different species, and also down the bottom for a mixed meadow. So if you're not so worried about individual species, but you're worried about the biomass of your meadow as a whole, rather than the composition of it. So they're available to assist in modeling impacts. If you can model your light regime, then you could apply it and use these sorts of thresholds to estimate effects. And that could help you to define zones of impact, as a few talks have mentioned so far. Second piece of work was Simone Striden's PhD, and Simone will present this in detail tomorrow. Sorry, Simone, I'm giving you one slide here. When you go under a dredge, that's a dredge plume, that's the sort of color you see, this sort of yellowish brown color. What we wanted to know was whether this change in color of light, the quality of the light, has an effect on seagrasses, because this was quite an unknown. So Simone did a series of experiments. In the first one, she subjected them to monochromatic light treatments, so very extreme differences. And she grew them under red, yellow, blue, green, and full chromatic light treatments. And what she showed was that very clearly, yes, seagrasses are affected by changes in light quality. There were some growth variables and there was reproductive variables that were affected by changing the light quality. Of course, that's not very realistic. So what she then did was manipulate the LED light source to produce a light spectrum that reflected one measured in a dredging plume off Onslow. And when she did that, basically the end result of that experiment was that the changes induced by that dredging plume did not produce negative effects. The reduction in light did, but the change in light quality didn't. So our conclusion there at the moment is that, and a major conclusion of her PhD work is that probably the focus should remain more on the effect of dredging in reducing the intensity of light rather than the spectral quality of light. Although, I will emphasize again, this was for one particular dredge plume, one particular spectrum, and one species. So more work to be done there. And the third set of experiments we did looked at the burial effect of dredging. So we subjected plants to different levels of sediment. We dumped this sediment on them in one hit, okay? Between 0 and 7 centimeters of sediment were dropped on them in one hit, and then we measured and followed them and saw what happened to them after that. The basic result was that, much to our surprise, up to 4 centimeters of inorganic sediment being dumped on top of a seagrass didn't do anything to them. Okay? And the reason is basically because, well, it did do something. It encouraged them. It's very difficult to see it in this photograph, but that black bit is where the vertical rhizome or the rhizome of the plant was at the start of the experiment. And basically, they rapidly grow up, and then they start growing across the surface again. So they're able to grow up through that sediment depth, get back up to the light, carry on growing, and we didn't really notice any significant differences in most of the things that we looked at. We were surprised, but there you go. We then ran a second experiment to sort of say, okay, well, some of the questions that have been posed to us were, what happens with interactive effects? Will you get the same effect if this plant is grown under low light? Because maybe under low light conditions, it doesn't have the storage reserves to support that vertical growth to get back up and cope with the burial. And does the type of sediment that is burying it matter? So in the second experiment, we grew them under low light conditions, and we buried them with inorganic sediment, but also with sediment which had 4% organic matter put into it. And basically the key result here is at 40 centimeters, which over here in inorganic sediment had no effect. In the low organic matter treatment, no effect, but in the organic enriched sediment, we had a significant reduction in shoot density. So conclude from that that under low light and in organic sediments, in organic rich sediments, then there was an effect. And so again, we've recommended a threshold around that 40 millimeters of burial for 6 weeks if you're in low light conditions with an organic rich sediment. Now, I'll emphasize here, that's a fairly limited interactive experiment, but it does suggest that the interactive factors are really important for us to look at. I'll also emphasize, as I think 2 or 3 of the talks have, we really don't know whether seagrasses will ever experience that condition. Okay, the field data on sediment deposition is almost non-existent. So how realistic that is, we don't know. The sorts of calculations that we've been doing suggest that it's not all that likely that you would see that, and if you did, it would be very close to the dredging. So the implications of this are that for pre and post development surveys, understand what seagrasses are at your sites, because different seagrasses respond differently to these pressures. It will help you to design your monitoring program, which bioindicators you want to use, and which thresholds you want to apply. And ideally, you'd look at the light environment, the sediment type, burial rates. From an impact prediction and management perspective, we've been able to recommend bioindicators. We've been able to present those thresholds. They could be used in modelling to also help you delineate your potential zone of impact. The findings can help with designing your dredging program to the extent that we'd recommend short periods of light reduction followed by longer periods of moderate to low light reduction are likely to reduce your impacts. And also that probably the emphasis should be on reductions in light intensity rather than light quality. Okay, I've only got a few minutes left, so I am going to zip past that because you can get all that tomorrow. One of the final pieces of work we did was that Catherine did quite a bit of work on the genetics of these populations up there. So just using one example here of Hologila uninervis, by looking at the genetic diversity within these populations, we're able to try to get an estimate of how resilient they were likely to be, working on the assumption that high levels of genetic diversity is likely to give plants a greater ability to resist or recover from impacts more rapidly. Catherine also used that genetic data to have a look at the amount of connectivity between different populations. So if one population was wiped out, how likely is it that seeds or fragments would come into that population from another population to help with the recovery? What we found is that connectivity is high at small spatial scales, 2 to 5 kilometres. Genetic diversity, some sites are very high, suggesting there's lots of sexual reproduction going on, and these sites are likely to have a high capacity to recover. But at other sites, same species, nearby, it's extremely low. And we have encapsulated that into what we're calling a genetic resilience assessment, which, depending on the sorts of measurements you take, you could use to give yourself some idea of the level of risk for your population of it not being able to recover following a major disturbance or not being able to recover in a reasonable time frame. So just to finish up, I think at the end of theme 5, we've greatly improved our understanding of seagrasses in the northwest. We've been able to develop bioindicators, impact thresholds, the resilience assessment framework, and we've got a better insight into the role of light quality. And we've been able to package that up into guidance on pre-development surveys, impact assessment, and post-development surveys for impact validation. Thanks very much.
This is where you finish then, Paul, because the next bell would have been the diving bell, I think. Any questions for Paul?
Paul, what's the effect of water temperature that is known to vary quite a lot over the seasons on the sensitivity of the seagrasses?
We haven't tested it explicitly, Paul, so I'm sort of guessing and going off the other published literature. My expectation would be that because of the additional respiratory demand it would put on them, that they would end up coping less well with the sorts of pressures that we've put in here. But Catherine or Gary may want to comment on that as well.
Or may not.
Or may not.
Of course.
Any other questions, Gary?
You put up there November through April or February as your time for the Pilbara. That probably wouldn't be a suitable time for
No, and you're right, Gary. One of the things, because there was so limited time, I didn't want to crowd the slides with lots and lots of conclusions. In the talk tomorrow, one of the things I'll point out is that some of the findings were that we should not assume that the Kimberley, the Pilbara, and the Gascoyne are similar, are the same, and will behave the same. We need to treat the three as different regions in terms of the natural plant dynamics, and therefore the context in which dredging could occur. And I think your work in the Kimberley has shown that it's quite different to what we're seeing in the Pilbara.
Any other questions?
Any idea how much seagrass has been lost due to dredging?
No.
Okay.
No. No idea. Paul, it's almost impossible up there to do it. You go to a site, the site that ended up with the greatest abundance of seagrass, the first time we went there to try to decide whether it was a suitable site for the monitoring and the assessments, there was nothing there. Previous information had told us that there was seagrass at this site. So the stuff is coming and going all the time. And that's why we're suggesting that the pre-development surveys, you need to do many of them, and ideally over multiple years, to give yourself a good sense about whether this is a seagrass site or not. And because that's a fair investment of time and money, we've put other guidance in about what are the sorts of things you want to be looking for when you're designing those pre-development surveys.
Michael?
Okay, Paul, where did your light thresholds fit into Rebecca's pressure gradients in terms of light distance from dredging?
I don't know, I can't tell you. Having seen Rebecca's stuff today, I think it's part of the next step. We really need to start to get this stuff coming together. What I can tell you very clearly is that at the sites, and I'll show this tomorrow, at the sites where we analysed the light, and where we did our own light monitoring. There was only, in the worst case, there was only about 6% of daily recordings did a day fail to reach the threshold that is required for plants to stay in a healthy condition. So at the sites where seagrasses are occurring, they're almost always getting plenty of light. It'd be very interesting now to match it up with the sort of light data analysis these guys have done and see if seagrasses were at these sites, which they're not, and if we get and adjusted for depth, what would we get? Yeah, it'd be a good thing to do.
Last question.
It's almost a generic question, but I worry a little bit that we're talking about sites that have seagrass as all being the same, and they're clearly not. And so I'm interested in why they aren't and what's the significance of their difference. Because at the moment we're at risk of, if the seagrass there, we might treat them in this way, and I think that's almost certainly completely inappropriate. So what leads are they into why, you know, if there's a site there and grass grows, it's not a lawn, right?
Yeah. Right. If you're thinking that way, then we've achieved exactly what we wanted. Yeah, people shouldn't be thinking about all seagrass sites as the same. And the pre-development surveys, it's important to understand what's there and therefore adjust your thresholds and your impact prediction according to what is at that site, not some generic seagrass thing. So you might want to use Samadosia thresholds at this site or mixed meadow thresholds at another site. The reasons for the variability, well, as many as there are ecological factors. Cyclones, I think, and major disturbance events, I think very clearly evidence is showing us that that's critical. It can wipe it out completely. 4 or 5 years later, you may have highly diverse and very abundant seagrass meadows. And in between those times, it'll be all over the place, changing composition. Grazers, water depth, water temperature, hydrodynamics. Catherine did a nice analysis on the factors that affect light availability at the site, and they're numerous in terms of the significant factors. Wind direction, time of year. Some of the meadows are naturally persistent, and others are transitory. That's just the nature of those meadows. Same species, different. So, you know, a wide range of factors. The take-home message is the one you said, that you just can't assume that it's a generic seagrass.